All right, so let's start with the next chapter on AC to DC converters in our power electronics course. So in this chapter, in this lecture, we'll be talking about half-wave rectifier, a single-phase half-wave rectifier, controlled and uncontrolled rectifier for different types of loads, we'll see. As you can remember from the first lecture, we discussed about various types of converters in power electronics. So to start with, we'll be discussing about this power converter, which is AC to DC power converter, which is also known as a rectifier. So the purpose of this rectifier, which takes AC as an input, to produce an output which is purely DC. So it can be rippled DC, means having some ripples superimposed on the DC, or it can be no ripples in a DC component, so we call it a purely DC. The other purpose is to produce a voltage or current as specified or having a specified DC component. Means based on the specifications of an application or as required by the application. So to get a specified DC component at the output, we can have different types of rectifiers. In this particular topic, we'll be discussing about half wave only. So uncontrolled rectifier uses diode as a switch. And if we want to attain the target or attain the specified DC component at the output, we can go for thyristor-based half-wave rectifier, where this thyristor replaces the diode as a switch. So if we use thyristor as a switch, then we can control these output levels, DC levels. So that's why the name controlled rectifier. So in that case, once the load and source parameters are fixed, so based on the application or the requirements of an application, the source and load parameters are already fixed by the specifications. Then the DC level of the output and power transferred to the loads are fixed quantities. Means then we can easily calculate all these DC output, average output, RMS output, or power delivered or power absorbed by the load, we can easily find it out. On the other hand, regarding the controlled rectifiers, so there is a way to control the output. So for that, we just use SCR or any controllable device. Referring to our first lectures or second or previous lectures, we discussed about various controllable switches also. So thyristor is or SCR is one of them. We can also use MOSFETs as a controllable switch, BJTs, and so on. We can use all these switches for a controllable rectifier. So as far as this course is concerned, we will be discussing about the thyristor-based rectifiers. So for that, two conditions need to be fulfilled. First one is the SCR must be forward biased. So means anode should be more positive than the cathode. So first, in a circuit, the thyristor must be forward biased. Once it is forward biased, then the gate signal must be applied to the gate of a thyristor. at any particular point of omega t axis at any instant. So once that gate signal is applied to the thyristor starts conducting. And at that particular instant, as we discussed in our switches lecture, at that particular instant where the SCR is given a gate pulse, that particular time instant is called firing angle and denoted by alpha. So first it should be forward biased. Second, it should be fired at an angle alpha so that the thyristor starts conducting. Now, putting these two half-wave rectifiers side by side, the reason is just to show that, okay, just by replacing diode with the thyristor or vice versa, we can just convert controllable into uncontrollable and vice versa. So let's say this, on the left hand side, we have an uncontrolled rectifier which produces a fixed output, which is DC, just because of diode. So by using diode, we can have a fixed value at the output. So as soon as the diode gets forward biased, it starts to conduct. So we cannot have any control. On the other hand, if we replace it with the SCR, this SCR is now this another extra or additional circuitry is required to control the gate signals. So this voltage source is connected to this load through SCR now. So in the positive, we know that this SCR is forward biased. But as soon as the diode is forward biased, it starts to conduct, and the complete voltage source is now appearing at the voltage at the output. But as soon as the thyristor is forward biased, this voltage, complete voltage or positive half cycle, does not appear at the output because it is forward biased, but it is not conducting at the moment. So we have to apply the gate pulse over here to make this SCR into conduction. As soon as the gate signal is applied to this SCR at an angle alpha, which is called firing angle, the thyristor starts to conduct, and we have a output at the load. To make it more clear, let's have this circuit, a half-wave rectifier using diode as a switch. So if we are using diode as a switch, we can say it is an uncontrolled half-wave rectifier. So only one diode, so it means half-wave rectifier, rectification will be possible at the output. So in mode 1, we have a positive half cycle of this input supply. Due to this positive half cycle, the diode becomes, assuming it as an ideal diode becomes forward biased, it starts to conduct, and now the current starts to flow in this load and a voltage is developed over here. So, which is shown by this waveform. And current is also shown by this waveform, which is this maximum peak value over here, Vm, dividing by the load resistance value at the load. So this waveform showing the current. But in the negative half cycle, mode 2, this diode becomes reverse biased. So it becomes open circuit. So no voltage is now appearing at the output. So zero voltage at the output because of the switching off of the diode. Same way, no current will flow, so current will also be zero. The complete negative half cycle will be applied across this open circuit now, which is shown here. So in that case, using KVL, we can just say Vm sin omega t is equal to current flowing in the resistance, giving this the voltage drop, which is equal to the resistance value at the load multiplied by the current flowing in the circuit. So as we can see from the equation below. So based on these waveforms, this only half of the cycle is received at the output. The other half is clipped out. So based on that, we can find out the average value of this. Graphically, the average value looks like this. So these alternating peaks are called ripples. And how to calculate these average and DC values analytically, we'll see in later slides. Okay, before going to the, we have already discussed about the harmonics and then the use of Fourier series. We can apply Fourier series for harmonic analysis. So in this case also, because this one, the ripples are kind of AC components because they keep on changing. And they are actually superimposed on the DC component. And due to the AC components being superimposed on the DC components, they cause harmonics because of the ripples. So for that, we can analyze the AC content, the AC harmonic content of the DC component using Fourier series. We'll do that at the end of this chapter. But okay, that was the analysis part, that using Fourier series, we can analyze the content of ripples in the output. But how to get rid of these ripples? Simply, we just need to add a capacitor at the load. If we add a capacitor in parallel at the load, we can smoothen out these ripples. Simply saying that in the positive half cycle, the diode is forward biased, it starts to conduct. And once the diode is conducting, the current starts to flow in the resistance load. And when the current is flowing through this diode, the capacitor starts charging if it is initially uncharged. So the capacitor starts charging in the positive half cycle. And as soon as it is fully charged and the diode is reverse biased in the negative half cycle. So this supply is now disconnected from this circuit, C and R. Now this charged capacitor will start to flow the current through this resistance. So it means now in the negative half cycle, the current in load is not zero now, as we saw in the previous slide. Because now capacitor is actually giving or releasing the current through this resistance. And depending upon this is how the current is being released. The charge stored in the capacitor is being released at the load like this. If depending upon the resistance and capacitance value, we can decide upon the RC constant. And if RC constant is large enough, then the discharging of the capacitor will be very slow and smooth. If the RC constant is very small, the discharging of the capacitor will be very fast. So the more amount of ripple will be seen at the output. So depending upon the capacitive value, the value of the capacitor and the value of the load resistor, we can decide upon the smoothening of the ripples. Smoothening means removing the ripples. So just by adding a capacitor, we can actually remove ripples, not 100%, but we can add other parts or other components in this circuit to get a smoothened output or a pure DC output. So this is a way of reducing the ripples. And analyzing the ripples we'll do at the end of this chapter using Fourier series. Okay, so that was the uncontrolled rectifier, means a diode rectifier having a resistive load, pure resistive load. Now this is a controlled rectifier, half wave rectifier, using thyristor instead of diode, and still for pure resistive load. The concept is same, positive half cycle, the thyristor becomes forward biased, but it starts to conduct only when the gate signal is applied. So let's say the gate signal is applied at angle alpha, omega t equal to alpha. Now the second condition is also fulfilled, so the thyristor can start conducting now. So thyristor starts conducting due to the forward bias in positive half cycle and due to the firing pulse at the gate at angle alpha, the thyristor starts conducting, and now the voltage is appearing at the output. So the voltage appearing at the output will be only after angle alpha, because before that the thyristor was off. So just by changing the value of alpha, we can change the output. So the larger the value of alpha, means larger the firing angle, it's also called delay angle. So larger the firing angle alpha, smaller will be the DC output. Smaller the angle alpha, larger will be the DC output. So we can change the DC output levels just by changing the angle alpha. So hence the name controlled rectifier. We can control just by controlling the gate pulses. Okay, to compare these two mathematically now. So to find out the average voltage for controlled and uncontrolled rectifier, by definition, we know that the input supply or the voltage signal over here is Vm sine omega t. We know that that was the source voltage over here. So that voltage signal is integrated from alpha to angle pi, because from pi to 2 pi the output is 0. So from pi to 2 pi output is 0 for half wave. So we can only take alpha to pi. So at alpha, the thyristor starts conducting, till pi it is conducting, and it keeps on integrating the voltage. And this integration, when it is divided by the total time period, we get a mean of that voltage. All instances integrated together from alpha to pi, dividing it by the total time period, we get a mean, which is average. So that average value will be seen at the output, also called DC value if we remove the ripples. So at this moment, we are not talking about ripples, we are just calculating the actual average value. So after solving this integral, we get this value Vm by 2 pi 1 plus cos alpha. But for uncontrolled diode rectifier, this voltage signal is same, but it gets integrated from 0 angle to pi, because the diode starts conducting at 0 immediately. So it gets integrating, this voltage that gets integrated from 0 till pi, and then dividing it by the total time period, we get an average. So looking at these two equations, we can see that just by substituting alpha equal to 0, this controlled rectification equation can be converted into uncontrolled rectification. So if you know these equations for controlled rectifier, just substitute angle alpha equal to 0, you can get the answers for uncontrolled rectification. Now same is applicable for RMS. As per the definition, the voltage signal squared, taking an average or a mean, dividing it by 2 pi, and then taking a square root. Now that integration Now that integration, which is summation, we can say, so that integration has to be again from alpha to pi. But for uncontrolled rectification, it has to be alpha equal to 0, because immediately it starts to conduct. Now, once we know these average and RMS voltages, we can easily find out the currents just by dividing it with the resistance at the load, because it is pure resistive load. So we can easily find out the values of currents. And value of power consumed by the load is also easily found out just by I square R, because we know that the power dissipation or power consumption at the load is I square R. So the current actually flowing in the load, in this particular case, it is the resistance. So current flowing in that resistance produces heat for some time, if we take it for some time period. So same way we can find out the power over here. So the only difference, again, I'm repeating, that substitute angle alpha equal to 0, we get an uncontrolled rectification. And if we have some angle alpha, any value, then that is a controlled rectification. So this is an example, a solved example I'm showing you. This one, again, the average value. The single phase half wave rectifier has purely resistive load, we saw that, and the delay angle means a firing angle of 90 degrees, pi by 2. So it means it is a controlled rectifier because it has a firing angle not equal to 0. If a firing angle is equal to 0, it means it is an uncontrolled rectifier. So angle equal to pi by 2. So you can easily find out using that equation, this equation. So integrate the voltage from alpha to pi, dividing it by 2 pi, we get this value, and we can substitute these values here and we can find out the average DC value. So using that, alpha is pi by 2. So you just use, if we know the value of Vm, we can easily find out the total DC voltage at the output. So from here we can see that the DC at the output is only 15% of the peak to peak voltage or peak voltage. Same for current, VDC divided by R, we get the average current at the output, which is DC in nature. RMS, again the same thing, integrating it from alpha to pi and then taking a square, dividing it by 2 pi and then taking the square root, we get this value. And once we know VRMS, we can easily find out current RMS. Second example, half wave rectifier circuit has this voltage supply, voltage source, and the load resistance is 15 ohms. So we need to determine the load current, average or DC load current. So in this case, VO by R means output voltage divided by the resistance, load resistance. We can easily find out the value of the load current, which is average current, just by using the formulas we derived here. And RMS also we can calculate just like this. And once we know this, we can easily find out the power dissipation or power consumption or power absorption at the load. And this is the power absorbed at the load, I square R, always in watts. But the apparent power is in volt amperes. Voltage in RMS and current in RMS, both multiplied together, we get a volt ampere. So based on this apparent power and the actual power or active power, we can easily find out the power factor. So the active power divided by the apparent power, we get 70% of power factor. This one, just continuing it, this example, which we did in lecture 2, talking about duty ratio. So a power converter is there having an input voltage of 20 volts. The output voltage is 12 volts. Calculate the duty ratio and pulse width if the switching frequency is 200 kilohertz. Very simple. This output voltage is given as 12 volts. Duty ratio is, we calculated there in our lecture 2, that output voltage is always input voltage multiplied by the duty ratio. For this moment, you must understand this thing. And later on, when we do with the DC to DC power converters, we can do it in detail, that how duty ratio is actually measured. So output voltage is equal to input voltage multiplied by the duty ratio. We get duty ratio of 0.6. And the switching time, because switching frequency is 200 kilohertz, taking a reciprocal, we get a switching time. So turn on time of this actual device, actual switch, the turn on time is duty ratio multiplied by the switching time, which is 3 microseconds. So for 3 microseconds, the switch is on, and remaining 2 microseconds, the switch is off. And 5 microseconds is, we can calculate directly from the switching frequency. So this is the time period of 5 microseconds. And based on this 5 microseconds of time period, 60% of the time it is on. Duty ratio is 0.6, means 60% of the time it is on. So 5 multiplied by 0.6 is 3 microseconds. So it is on. Rest it is off. 5 minus 3. Same, you can solve this example using these formulas which we did earlier in our example 1. Same formula is used for DC output or average output. So same formula we can use for the calculation of VRMS. So you can solve this very easily. Okay. So now the next step, if we have a inductance present in the load, so how the behavior is for this half-wave rectifier circuit? Because we know that in practice, the loads are normally not pure resistive. They have inductance also. So in practical applications, resistive and inductive load is present almost in all applications, industrial applications. In all industrial applications, we have inductance present in the load. Medical equipments, going to the hospital, there are all medical equipments. There also a huge amount of inductance is present in the load. And lab equipments, and in other day-to-day life, like IoTs, different IoTs connected together, different wireless systems connected together, they all have inductance present in the load. So if we have inductance, what is the influence of this inductance in rectification? So this we need to learn in this chapter. So again, the same thing. If we know the working principle of a controlled half-wave rectifier, we can easily relate it with the uncontrolled by assuming alpha equal to 0. Okay, so let's say we have again the half-wave rectifier circuit, but the only one additional element over here is the inductance. So at the load, R and L both are present. So that's why it is called RL load. So this half-wave rectifier, again, we'll be working in 2 modes, positive half cycle and negative half cycle. So in positive half cycle, let's start with the positive half cycle. This is the supply. This Vm sine omega t is the supply input, supply voltage or a source voltage. So this sinusoidal input is given to this half wave rectifier circuit. So in the positive half cycle, the thyristor now becomes forward biased. So first condition is fulfilled. Now, as we move on, now the thyristor is fired at this firing angle. Means this pulse, this rectangular pulse showing over here is the firing pulse at the gate. This firing pulse is applied at the gate for small instant of time. And the gate current will start to flow. And once the gate current starts to flow, the thyristor will be on. And we know that from the characteristics of the thyristor, if now the gate pulse is removed, still the thyristor will continue to conduct. Okay, so the gate pulse is applied at the gate at angle alpha. So we know now the second condition is also fulfilled. First condition was that the thyristor must be forward biased. Second is that the gate current should also be applied in order to turn the thyristor on. So now in the first one, it was only forward biased. So condition 1 was fulfilled. Now condition 2 is also fulfilled because of the firing pulse applied to the gate. The thyristor starts to conduct, so it turns on now. So when it turns on, it starts to conduct. Now the voltage at the input over here is now appearing at the output over here. So it can appear at the output. So we can see from here the load output, the load voltage is showing the voltage over here. Because here the thyristor was not conducting, so it was open circuit, so no voltage was appearing at the load because of the open circuit. Now it is conducting, so this voltage is now, it starts appearing at the load. So we can see from here. About the current now. Because of the presence of inductor in this circuit, the current starts to flow slowly, because we know, as per the characteristics of inductor, it opposes the flow of current. So it takes time for the current to flow in an inductor. So the inductor will start to flow slowly. So it increases in a finite time, slowly in a finite time. Now next, because the thyristor is already on now, still we are working in the positive half cycle. Now the current starts to grow over here. Because of this inductor, the increase in current is gradual, not abrupt, but gradual. And we know that as the current starts to increase gradually in inductor, the inductor starts storing the energy. So it starts storing the energy. So energy is being stored in the inductor. So now, when we reach angle pi over here, the supply voltage reverses, means now the negative half cycle will start. But still the thyristor keeps on conducting. In pure resistive load, we saw in earlier slides, the thyristor stops conducting as soon as the negative half cycle starts. The thyristor stops conducting because it gets reverse biased. But in this case, the thyristor continues to conduct because of the presence of inductance in the circuit. At angle pi, the thyristor becomes fully charged or fully energized. We can see from here. And the voltage at angle pi reaches 0. So it reaches 0 over here and it reaches 0 over here. But the current still continues to flow. Now, as the polarity at the input reverses, the polarity in the inductor also reverses. And due to the reversing of this polarity at inductor, this negative becomes positive, positive becomes negative. So due to this, because it downplays this voltage source and larger positive polarity is seen over here, and the thyristor is again forward biased and it continues to conduct. Now this inductor which was energized during the positive half cycle, it reverses its polarity in the negative half cycle, and now it starts to flow the current in this direction, and this thyristor is kept on, it keeps conducting. So it means whatever energy was stored during the positive half cycle in inductor, now it starts to de-energize because it is now releasing the energy through flowing the current over here. So it starts releasing the energy over here. And we can see from here, as soon as it starts releasing the energy, the current starts to decay in the inductor. Whatever charge it has stored over here, it starts to discharge. So the current starts to decrease or decay in the inductor. Here the current was maximum at angle pi, so fully energized. Now it starts to de-energize, and now the current starts to fall in the inductance. Energy stored is now being released and flown in the resistance over here. So it means this inductor starts to get de-energized and the inductor current becomes zero. So where the inductor current becomes zero means now the inductor is fully de-energized. Whatever charge was stored in the inductor during the positive half cycle is now fully emptied, fully released. So no current, no charge in the inductor. So at that particular point, at omega t, where the current in inductor becomes zero is called extinction angle. So that particular point at which the current in inductor becomes zero is called extinction angle and denoted by beta. So omega t equal to beta, the current becomes zero, and now the thyristor turns off because it is not forward biased anymore. So the thyristor turns off. So at angle beta, the thyristor turns off, and now when thyristor turns off, no voltage will be applied at the load over here. So the voltage also becomes zero. And then it continues to be zero because the thyristor is still off. It is still off, so it continues to be no voltage at the load. And the current was already zero at angle beta. And at angle beta, the thyristor turns off. And when the thyristor turns off, still no current will flow till we have a next cycle. So in that case, voltage also continues to be zero after beta till 2 pi. And current also continues to be zero because of the open circuit of a thyristor till the next cycle. So whatever voltage in the negative half cycle we have, because it is turned off now, the complete voltage will be applied across the thyristor, we can see from here, until it is fired again or a gate pulse is applied again. So in that case, we can say that the current, the behavior of this inductor shows us that the current can continue to flow after angle pi also. So in that case, the conduction period is increased if we have inductance in the load. If we have a larger value of inductance, the conduction period can increase even after this. So we can increase the conduction period which is from alpha to alpha plus, pi plus beta. That is the conduction period. From here, alpha, where it starts to grow, and where it goes to 0, we have this conduction period, and this conduction period can be increased by increasing the value of inductance. Okay, now graphically we have seen that how the behavior of this half wave rectifier at a RL load. Now analytically, how to do it. So analysis, again, assuming the thyristor is on at angle alpha, we know that because at angle alpha we apply a gate trigger. So this angle, again, it is called firing angle. So now using KVL, so assuming this thyristor is turned on now at angle alpha, what is the KVL? So this voltage is equal to the voltage drop here and here. So you can see in 4.1. So voltage source equal to voltage drop in resistance plus voltage drop in inductance. But due to the presence of inductance, this equation cannot be solved straightforward. Because we know that due to the presence of inductance, the current cannot shoot up immediately or it cannot go down immediately. It takes time to develop, reaches maximum value, and then it takes time to decay and go to the 0 value called steady state value. So due to this particular nature, we can say that the response of this inductive load to this input supply due to the presence of thyristor is a superposition of forced response and natural response. We'll see that, what is forced response and natural response. So natural response, also known as transient response. And we saw that in the graph of over here, we saw that it takes time to reaches to the maximum value and it takes time to reach to the 0 value. So that is a transition time. So called a transient response. So that is a kind of a transient response, means it takes time to respond to the particular stimuli. Stimuli is the input Vm sin omega t, or excitation. We can also call it excitation because we are actually exciting the circuit by applying the Vm sin omega t, or we are providing a stimuli to it. So by exciting this circuit, we detect the response, or we sense the response of that particular circuit, that how this particular circuit responds to the particular excitation. And we saw a transient nature, taking some time, finite time, to reach to some specified value. So that is due to the natural response. But we know that it takes time to develop from 0 to maximum value, and then it reaches maximum, and then it goes to 0, and it takes time, and then it remains at some 0 value. So it means that transient response is temporary in nature. Because for small time, the gate trigger was applied. For a small time period, the gate trigger was applied. So some stimuli was applied to the circuit, some excitation. And then slowly it was responding, reaching the maximum value, and slowly it was decaying to reach the 0 value back again. So it was temporary in nature. So that response also we have to take into consideration. The other one is the forced response, which is called steady state response. So means after this transient behavior of the circuit, it reaches to 0 and then it stays at 0. So it means after transient behavior, a steady state behavior will be seen, so that it settles to the specified value. In this case, it is 0 for simplification. So settling it to the specified value. And it remains there. So hence, it takes time. And then it takes time for the next cycle to get excitation. So steady state, it can stay in steady state for a longer period. But now due to this presence of inductor in this particular circuit, we have these two behaviors superimposed on each other to get a final response. So graphically, what I just explained, graphically, if I can show you, so this is a transient behavior, decaying from the maximum value reached. So maximum value reached for the inductor current, and then it was decaying to 0 slowly like this. So this is a transient response, which is natural due to the physical phenomena, due to the nature. Superimposed, plus sign shows superimposed on the forced response. So this is a forced response. Forced response means we applied a sinusoidal stimuli, Vm sin omega t, that we applied as an external source. So we are actually forcing the system to behave, to show behavior on Vm sin omega t, and which was at the output only one half of the wave is shown, otherwise other is clipped. So we are actually stimulating or exciting this circuit with a sinusoidal input. So this is a forced external excitation. So when we superimpose these two, we get this type of a behavior. Initially, it was, because this is superimposed with this, we have a high peak over here. And then this peak goes on decreasing because of the natural response, transient response. So it goes on decreasing and decays to 0. So it decays to 0. And it goes into a steady state. And that's what we want. So steady state means only simple sine wave, no ringing is allowed over here. So this is only due to presence of inductor. Now mathematically or analytically, how to do that? So the steady state current can be found from phasor analysis. We know that Vm sin omega t was already applied at the input, having some, so theta can be a phase angle because of the presence of impedance over here. If this Z is equal to R, then theta will be 0. We know that. But due to the presence of inductance inside it, there will be some phase angle. So that's why the input stimuli, this one, the current due to the input excitation, which was Vm sin omega t, and due to the presence of this inductance, we divide it by impedance, we get current. And due to the presence of this impedance, we get an angle alpha also in the current. In voltage, we do not have any angle, but due to the presence of inductance in impedance, and we get an angle, this one. So this impedance is, we know that R square plus omega L square, and this phase angle is tangent inverse of omega L divided by R. So now about the natural response. So natural response, we know that it is without any external stimuli or without any excitation, means which happens naturally without any external force. So equating this from 4.1, we saw that this 4.1 equation, this voltage source was applied, and when this thyristor was on, so we get a KVL, which is equal to voltage supplied equal to voltage drop plus voltage drop. So same over here. Now voltage supplied is 0. So equating this to 0, we have this, and we can solve it using the differential equations. So solving first order differential equation, we can get this. So now this current which we found out from here by differential equation solver, we get this current. Now it is known as a natural current, natural response to the circuit. So this is now exponential in nature. We know that using the differential equation solver. So this exponential nature of this natural response, we can from here see that this value of this capital A gives us the amplitude. So this is the amplitude. So at what point it was maximum and it starts to decay. So this angle A, this value of A, which is amplitude. An exponential of minus t divided by tau. Tau is the time constant. So depending upon the value of inductance L and R, we can decide upon the value of the time constant. Larger the time constant, slower will be the decay. Smaller the time constant, faster will be the decay. So faster it will, or very small time it will reach 0. So minus sign over here shows decay. So this natural response will show us the decay over here. So transient in nature. So from 4.3 equation and 4.6. So 4.3 was Vm by Z sine omega t minus theta, which was the natural response, forced response. And natural response is this one, exponential of minus t by tau. So both are superimposed, and now we have that equation 4.7. So once the superposition was done, and we know that now it is the behavior of this circuit to the input stimuli. So now to find out the value of A, if we want to find out the value of A, that what was the maximum value from where it starts to decay. We put angle alpha. So at omega t equal to alpha, the thyristor starts conducting. And from there, we say that if initially no current was there, because only after angle alpha, the current starts to develop. But before that, it was 0. So putting this condition as an initial condition, we can find out the value of A, which is this one, equation 4.8. So before angle alpha, the current was 0. So taking that an initial condition, we found out the value of A. So now putting the expression of this A in 4.7, we get this. 4.7 was this. So putting the value of A from 4.8, we get this. And from here, we have an angle alpha over here. So just by putting the value of alpha to 0, we can use the same expression in case of diode half-wave rectifier, which is this. So we can easily convert this controllable rectifier into uncontrollable rectifier by putting the value of alpha equal to 0. So this is the superimposed value. So this is the actual response of a half-wave rectifier to the inductive load due to the presence of inductance in the load. Okay, so another parameter remaining now. Now the maximum value we have seen, we can calculate using, so that was denoted by capital A. Another value, alpha we know. Now the other remaining part is beta, where actually the current goes to 0. So substituting the value of beta over here. So at angle alpha also, the current was 0. Now at angle beta also, the current is 0. So putting omega t equal to beta, at which the current is 0, so we can easily find out the value of this current. So now using all these parameters, this is the final response. So this is the final response of the half wave rectifier when we have a inductive load. This one. So this current, this expression of current will flow only between alpha and beta. So it means this mathematical expression is this one. So it starts from alpha. At alpha it was 0. At beta also it is 0. So from alpha to beta only the current flows. And that curve was, we saw it analytically. So this is how that curve can be represented mathematically. Before alpha and after beta, the current is 0. We saw that. So this is how that graphical representation can be solved analytically. So once we know the current, that current I omega t we know from alpha to beta, we put that value over here and we can find out this current, which is the average output current or DC output current, dependent upon angle alpha and beta. Same way voltage also, easily we can find out Vm sin omega t, alpha to beta, easily we can find out, as we have done in pure resistive case. In pure resistive case, it was alpha to pi, but in this case, it is alpha to beta. So that's the only difference. So an inclusion of parameter beta in case of inductance in the load. And current again I'm saying, so substitute this value 4.9 I omega t, which we found out analytically. So substitute this over here, and then between the limits alpha and beta, we get this. Same for RMS, we can calculate. So again, for diode rectifier, alpha can be put to 0, and we can have it. So this is example you can easily find out. So determine the expression for I omega t. You can easily find out this expression because all the values are given. And just substituting all these values in that particular expression, we get this. And average current we can easily find out using these formulas. Average current. And power absorbed we can find out I square RMS multiplied by R. And value of R given is this. So easily we can find out these values. So now, what are the problems or issues in the half wave rectifier if we are having a RL load at the output? We have seen previously in graphical representation that a negative voltage we see at the output due to the presence of the inductance. We saw that. So which is this one. From pi to beta, we have a negative voltage at the load. That is one issue. Another issue is that the current is discontinuous. Discontinuous means it flows from alpha to beta. In this case, it is diode, so it is 0 to beta because alpha is 0 in case of diode. So it flows from alpha to beta. So in this case, alpha is 0, so still I will be saying alpha to beta. So after beta, it goes to 0. So it means the current is not continuous in nature. It rises up, it goes down, and it stays down for some time, and again it goes up. So it is discontinuous in nature. So these are the two issues. And normally, if it is discontinuous in nature, we can see the ripples. Ripple means sometimes it is going up, then going low, and then again low, again up. So we see a kind of bumps, ripples in this case. That is also an issue due to the discontinuous current. So how to address these issues? One simplest method is to add a diode in parallel to the load. And after this diode, we can still have a capacitor, no problem. That due to the the reason is because we know that if we add capacitance in parallel to the load, we can remove ripples or because of smoothing of the charging and discharging of the capacitor. So that we can still add over here. But in this case, we need to find out the significance of this particular diode connected in parallel to the load in this direction. Anode in this direction and cathode in this direction. We'll see that how it will actually help. But before going further, we need to understand that these two diodes are mutually exclusive. Means both of them cannot be forward biased at the same time. If one is on, another one should be off, and vice versa. Okay, so now how actually the working principle works. For a positive half cycle, this is the flow of the current. So for positive half cycle, D1 is on and D1 goes off because a positive supply is connected to the cathode, so it gets reverse biased, so it is off. So in that case, for positive half cycle, D1 is on and D2 is off. So this circuit will be the equivalent circuit for that particular circuit, because this branch is now out of picture. That diode is now out of picture. So this circuit will be an equivalent circuit. So now voltage across this RL load is exactly equal to the voltage over here, because there is nothing in between. So no voltage drop. As per KVL, voltage supplies is exactly equal to voltage dropped at the load. So VO at the output is equal to VS at the input. Now in the negative half cycle, D2 is on, this is on. In negative half cycle, this is forward bias, this is on, now this is off. So by turning this diode off in the negative half cycle, this supply is now disconnected with this circuit. So now we are remaining with only this circuit. So only this circuit supply is now disconnected. So now whatever charge stored in the inductor during the positive half cycle is actually being released through this circuit, because now the diode has given it a path by turning it on, because D2 is on now, and if D2 is on, it starts to conduct, and due to the presence of energy inside this inductor during the first half cycle, now this energy is getting released from this inductor due to the conduction of this diode, and now the load still continues to get the current, and we get the output voltage over here. So means this diode is now actually helping us to conduct or to flow the current at the load. Due to this reason, it is called the freewheeling diode. It freewheels the current. Freewheels the current means without the presence of the source, it still helps us to flow the current. Freewheel, without any energy, without any external source. So due to this, in the negative half cycle, because this one, in the negative half cycle, the diode is simply turned on. No presence of supply over here. And if the supply is gone, negative half cycle is completely gone. So whatever we have at the inductance, we get at the output. So the negative half cycle of the supply is completely disconnected. So that's why we do not get negative half cycle as we saw in here. So in that case, the negative half cycle, the negative supply is removed now, clipped now. What about the current? Now, so it actually resembles this. This is the voltage waveform. It actually resembles the pure resistive voltage waveform as we saw in the very first circuit. So the presence of inductor will not have any effect on it by clipping the negative voltage supply. Now about the current. Current starts to flow due to the D1 because of the presence of inductance. The energy starts to be stored in the inductance during the positive half cycle. And the current continues to flow in finite time because in inductance, it takes time to develop the current, like we saw in the previous circuit. So it takes time to develop the current over here. And now it should go to zero, as we saw in the previous case in RL load for rectifiers without the presence of a freewheeling diode. It was decaying to zero if the freewheeling diode was not present. But in this case, due to the freewheeling diode, the current continues to flow through this diode back into the load. And if the value of inductance is larger, this can be even higher. Means the releasing of the energy can be slow and very less. So we can remove the ripples just by increasing the value of inductance. But due to this freewheeling diode, the inductor continues to release the energy, or the current continues to decay very slowly in gradual manner like this. It never goes to zero because of the continuous flow back of the current due to the freewheeling diode. So in that case, the current continues to flow till then. So this waveform of the current is called continuous current. So we have changed the discontinuous current into a continuous current just by adding a diode, a freewheeling diode. So from here also you can see, due to diode D1, the current was actually growing in finite time. And due to the presence of diode D2, the current is actually decaying in finite time, but very slow. It is never reaching zero. So that was diode when alpha was zero, but now when alpha is having some value, so at this point gate trigger applies. Now the thyristor starts to conduct and the current starts to grow from angle alpha in diode D1. And when in negative half cycle, this is off now, thyristor is off, diode D2, the freewheeling diode, will continue to flow the current. So due to diode D2, the current will flow, this freewheeling diode, and it keeps on going. The only difference is angle alpha. At angle alpha, the current starts to develop in the inductor. So no negative voltage at the load due to the freewheeling diode. So due to the presence of this freewheeling diode, a load current, when we want to calculate the load current for RL load, pure resistive load is very simple, not a problem. But if we have inductance present in that, so due to that, harmonics start to come into picture. So referring to our lecture on harmonic analysis or Fourier series, so this equation we can use for harmonic analysis. So this is the DC component. These are the sinusoidal coefficients, and these are the cosinusoidal coefficients. And we also saw a kind of a general form of Fourier series, which is equation 4.16, which is a simplified form of 4.15 and normally used in electrical engineering. So equation 4.16 is a general form of Fourier series, generally used in electrical engineering, where we have, this is the instantaneous output voltage, which is calculated using this formula. From 0 to pi, we have sine omega t, the input supply. From pi to 2 pi, we do not have any voltage at the output. If we have a thyristor, then the limits will change from 0 to pi to alpha to pi. And from pi to 2 pi, the voltage at the output is 0 because due to the freewheeling diode, the voltage supply is disconnected in the negative half cycle. So we do not get any voltage at the output. So this is the instantaneous voltage, which is equal to the DC component over here. This is the DC component plus summation of all the coefficients or harmonic components present in the voltage waveform or current waveform. So depending upon the value of n, we can decide the value of harmonic component. We'll see in that. So this simple model we know, and this switch is on, let's say, for a half wave rectifier, a supply, a switch over here, red part, a switch is there, and then the load. So this model, equivalent model, when the switch is on, can be redrawn as a model B also. Model B says that this instantaneous voltage, which is Vm sine omega t, can be broken down into set of components calculated using Fourier series. So the first component is the DC component, V0, pure DC. And then the first harmonic component, which is V1 cos of omega naught t plus theta 1. So omega t, we know the time axis having frequency of 2 pi f, plus theta is the phase angle. V1 is the magnitude of that particular harmonic component. So particular harmonic component, this is first harmonic component V1. Now V2 is the second harmonic component, n equal to 2, having the phase angle theta 2, and then so on. So we can add these components to find out the response at the output, at the load. Because all these harmonic components play an important role in giving us the output. And we need to find out which harmonic component has which magnitude, V1, V2, or V3. If V1, just to explain you, if V1 is equal to V0, it means that this DC component we want at the output is now, if we superimpose with this one, which is exactly the same value, then it means that on this DC component, a high amount of ripple is being superimposed, which we don't want. So we want to first analyze, and then we want to get rid of the higher magnitudes of these harmonic components. So before getting rid of these high magnitudes of harmonic components, we need to analyze first. We need to calculate the values first, so that we know that how to get rid of all this. So this model can be redrawn as model B, which are exactly the same, because in the previous one we saw V naught T is equal to summation of all these. So equation 4.16 can be represented like this. Model A is equal to model B. Now, how to get the response at the output due to all these harmonics, n number of harmonics present? We know we can use superposition theorem in that. And the superposition theorem, we know that only one source, we calculate the response of all the sources by activating only one source at a particular instant, and then summing all these responses together like this, summation, and then getting the final value. So this is a DC term, only DC source is connected. So we get the response due to DC component over here to find out the value, let's say for current, what is the value of current over here due to this. And then we calculate the value of this current I1T due to the first harmonic component. And we find out the value of IT, means how this first harmonic excitation will behave in this RL circuit. And then we keep on calculating individual currents due to individual harmonic present in this voltage over here or current over here, and then sum all these things up. How to do that? Better to do it in frequency domain. So transform the circuit into frequency domain, or you can say phasor form, and then solve these using some theorems or circuit theory techniques or circuit techniques. But in this case, particular case, we'll be using superposition theorem. And then once we analyze this, we can transform that particular phasor form or frequency domain into time domain again. Okay, first one, transform the following independent into frequency domain or phasor form. This we already know. So we need to transform this into the frequency domain. Frequency domains means that there are only two informations we have. For DC component, we have the magnitude, that how much DC value will be there and what is the angle. And for first harmonic, how much is the magnitude of that particular voltage signal or current signal over here, and how much is the magnitude of that particular voltage, and what is the phasor, what is the phase angle. So means we convert that into a polar form, and then we can easily find out this current in this impedance, and then solve these using superposition theorem. So this is the polar form of the voltage, the harmonics, dividing it by the impedance and angle theta, which can be easily be calculated using tan inverse omega L by R. So using this polar form, voltage dividing by the impedance, we get the current in frequency domain. Means in frequency domain, we only have two values. One is magnitude, another one is phase. And once that is done, we can convert that back into time domain. Again, coming back to the sinusoidal form. And then easily we can find out the, let's say, first harmonic content in current I1T. This is the first harmonic present in the current signal. This one. So just by calculating these, we can easily find out the magnitudes. And then we can sum all these together to find out the response. And if any one of them, let's say this second harmonic, after calculating, has a huge value over here, then it means that this harmonic is causing any problem in the form of a ripple or disturbance or distortion. So we need to remove this harmonic particularly, so that the output is smoothened out, or output becomes pure DC. So after calculating, we can decide whether to remove and how to remove and what type of harmonic should be removed to get a pure DC. So these are the examples. So this circuit is given. We need to find out power absorbed by the resistor over here in the circuit. So this is how we can do that. So this is the DC component over here. Just average value. We saw the formula, we derived the formula over there, and using that formula we can find out. And from this, easily we can find out the average current, because we want to find out the power absorbed in the resistance. So we can easily find out the power I square RMS into R. So if we want to find out the amplitudes of all AC components, we need to find out the impedance. And then once the impedance, then we can easily find out the phases also. So for this one, the AC voltage amplitude, we know that we can easily find out using that formula. And now all other harmonics can easily be found out using this, the 4.15. Equation given by 4.15, using that equation, we can easily find out the harmonic contents. So for second harmonic, put n equal to 2 in 4.15, n equal to 2, we can find out and calculate the value and all these voltage values. So from here we can see that DC component is having a 50 volts. Second harmonic is having 21 volts as a magnitude, which is sufficient, means quite considerable. Fourth harmonic has a smaller value, 4.24. And if we say, okay, we want to design a low cost circuit or low cost design, power electronic design, so we can cope up with this fourth harmonic. And sixth harmonic is very small, 1.82 volts. Very small compared to 50 volts of DC component at the output. So it means a DC of 50 volts supplies at the output, we can draw 50 volts line, DC line, and on the top of it, we can superimpose small sinusoidal components, 1.82 volt of a sixth harmonic. And if we go further with other harmonics, the values will keep on decreasing. So all these higher harmonics will have lower values of magnitudes, voltage magnitudes. So maybe they will not cause any problems, depending upon the type of application we have. Like for medical applications. For medical applications, small harmonic disturbance can also give us the false results. So in that case, maybe large number of harmonics needs to be analyzed and removed. But for simple applications like mobile phones, landline phones, or maybe even small other applications. So these harmonic contents can be okay, because we do not want to spend too much money on that. So depending upon the type of application, we can decide how many harmonics can be allowed, and after which harmonic we need to get rid of. And as I said, for medical applications, for aerospace applications, or life-saving applications, even small harmonic content can give us false results. So these harmonic contents can be removed. Even 1.82 is quite high in that application. So that also has to be removed using filtering techniques or other techniques. So this is how you need to calculate. And here this is simple Fourier that how these harmonic contents can be evaluated. So this is a half-wave rectifier, diode rectifier. So again, the same Fourier series representation. DC means DC component over here, and then sinusoidal and cosinusoidal coefficients. First, we calculate the DC component, which is Vm by pi, and then we calculate the sinusoidal coefficients, which comes out to be Vm by 2 and 0 for even harmonics. And then Bn means cosinusoidal coefficients we can calculate, and for odd harmonics it is 0. An is normally 0 for even harmonics, Bn is for odd harmonics. And we can calculate all these harmonics, harmonic components like this. So summation of all these, and we can calculate. So zeros, so these we can calculate, Vm by 2, and then rest all is this one, cosine components. So all the cosine components are present in half-wave rectifier. So we can just keep on putting the values of n equal to 2, 4, 6, because for odd it is 0, and we can find out these values over here. And then we can calculate these values if we know the frequency, just by substituting the frequency in this. And if we know the peak value, substituting these values over there, and we can sum all these things up, and we can calculate the individual harmonic content as well as the total harmonic content. If we calculate the total harmonic content by summing all of them up, we find out the total harmonic distortion. And if we find it individually, we can easily find out which harmonic content is actually causing problem. And it should be definitely removed. Okay, so with this, we have finished the half-wave rectifier, and we can now start with the full-wave rectifier.